And Professor LeCun has received many accolades of different kind. I will mention just two. He's a member of the National Academy of Sciences of the USA and the winner of the Turing Award, which is the highest award in computer science. And today, Professor LeCun will speak of the present and future of artificial intelligence. The present of artificial intelligence, which is glorious, which this is the time then, after many years of sort of not entirely fulfilled promises, artificial intelligence actually really works. To a large extent, we owe this to Professor LeCun's contributions. And I strongly suspect, and I think we will be compelled by today's lecture to believe that the future of the artificial intelligence, far more glorious beyond doubt, will also come in large part from Professor LeCun's contributions. I also have been told, more personally through word of mouth, that Professor LeCun is extremely inaccessible. It's extremely difficult to get hold of. So we are very lucky to have him here tonight. Welcome.
Thank you, Eugene, for this very nice introduction. I'm not hard to get a hold of. I don't answer email very well. That's the only thing I don't do. I get too much of it. Anyway, so let's talk about the present first of AI. And we've been hearing a lot about AI over the last 10 years or so, roughly, increasingly frequently in the press, in the media, industry, everywhere pretty much. And it's all due to, of course, progress in machine learning. So machine learning is a branch of AI, and particularly to a branch of machine learning called deep learning, which I'm sure many of you are aware of. And all of this is, almost all of this, at least until fairly recently, is due to the use of a particular set of techniques called supervised learning. So what is supervised learning? It's basically teaching a machine to perform a function instead of programming it directly to perform that function. So let's say we want to teach a machine to classify images of cars from images of airplanes. We collect thousands of images of cars and airplanes, and we show an image of a car to the system, wait for the answer. If the system says car, we don't do anything. If it says something else, we adjust the internal parameters of that machine, which are basically just a large collection of numbers, so that the answer gets closer to the one we want. Okay, so think of this learning machine as a mathematical function that depends on lots of parameters, and we're going to adjust the parameters so that we get the answer we want for a particular input. So we show the image of a car, then we show the image of an airplane, and again, if the answer is incorrect, we adjust the parameters a little bit. And then we keep doing this for thousands or millions of images, and eventually, if the machine is properly built, of course, it's not a real machine, it's a program on a computer, but eventually the parameters will settle on a configuration that will allow the machine not only to give the right answer for all the images we trained it on, but also for new images it's never seen before. It's going to be able to tell you whether it's a car or an airplane, even if it's kind of an unusual car, an unusual airplane. Maybe not the one in the middle here, that's really strange, but that's actually an experimental French plane from the 1960s called the Coléoptère. Anyway, I like airplanes. So this works really well for categorizing images, for doing speech recognition, translating speech into words, for recognizing faces, for generating captions for images, for classifying the topic of a piece of text. And for those of you who are technically inclined, the sort of mathematical formulation of this is one of function optimization. So think of, I show the machine an image of a car, and I tell it this is a car. I can measure a sort of distance or divergence between the answer that the machine produces and the answer I want. Okay, that's going to be a number. It's going to be 0 if the answer is correct. It's going to be a positive number of some kind if the answer is incorrect. And I can compute the average of this function over lots and lots of images. And the problem of learning really is to find a setting of the parameters of some mathematical function that makes this function take low values on the training set. Okay, so compute the average of the function over a whole bunch of images together with the desired output. That gives you an average cost distance of the answer from the answer you want. And then try to figure out the value of the parameters of the function so that this number is as low as possible. In mathematics, that's called optimization. And this is done using a very simple algorithm called the gradient descent, essentially, or something similar to this. And what gradient descent consists in, basically, is figuring out in which direction, in which direction should I tune all the knobs, all the parameters, so that my cost goes down. So imagine that you are in a mountain, in a fog, and you want to go back to the village, and you're somewhere in the mountain, you can't see the village because there is fog. And so what you can do is look around you for which way goes down, right? And then you just follow the path that just keeps going down, and eventually you'll find the valley, assuming that the mountain is relatively smooth. If it's got like ups and downs, you may get stuck. But if it's smooth, you're going to find the minimum and go to the valley. It's the same idea. So you figure out the direction that makes this cost function decrease as fast as possible, and you take a step in that direction. That's called gradient descent. Okay, so now the next question you have to ask yourself is, what am I going to put in that parameterized function, in that big box with knobs that I was drawing earlier? And what we've been using for a long time, but increasingly for the last 10 years, is what's called an artificial neural network. So artificial neural network is basically inspired a little bit by biology. The way the brain is constructed is that it's a collection, a very large network of neurons. The neurons are connected with each other, and when we learn, the strength of the connection between the neurons are modified. That's kind of the seat of learning, if you want. That's called synaptic plasticity. The synapses are the connections between the neurons. So with this idea, people in the 1950s kind of tried to reproduce this with either electronic circuits or with programs on computers. And then that made a big progress in the 1980s with the discovery of something called backpropagation, which I'll talk about in a minute. But basically, you take a whole bunch of simple mathematical functions that essentially compute a weighted sum of their inputs, and then compare this weighted sum to a threshold. If the weighted sum is above a threshold, you turn on the neuron. If it's below a threshold, you just turn it off. And the weights in those linear combinations are going to be the knobs that are going to be adjusted by the learning algorithm. Okay? So we're going to build large networks of those simulated neurons that perform a weighted sum and then pass it through a nonlinearity. So there is nothing more to modern AI systems than basically multiplications, additions, and comparisons. That's all there is. Okay? The programs to run those neural nets are extremely simple. What's a little bit more complicated is to figure out this gradient computation. So you have to figure out efficiently in which direction and by how much to change all those coefficients, all those weights in those weighted sums, so that the output gets closer to the one you want. And that's done with something called the backpropagation algorithm. You can ignore the mathematics, okay? Don't be scared by it. I'm not going to go through that. But it uses, for those of you who remember mathematics courses, it uses a rule in mathematics called chain rule. En français, règle de dérivation des fonctions composées. So very simple, something you learn in high school, essentially. So that's the only mathematical concept that we need for this. And basically what it allows you to do is backpropagate signals backwards from the output towards the input in such a way that for every parameter in the system, every coefficient in the system, compute the direction and by how much you need to change that parameter, that knob, so that the output gets closer to the one you want. Okay, that's called a gradient vector. So this was discovered a very long time ago in various contexts, but the application of this to machine learning is goes back to maybe 1986 or so. So not that old. Okay, and then the next question you have to ask yourself is precisely how are you going to organize all of those neurons? How are you going to connect them with each other? And there, you can get inspiration, another set of inspiration from biology by looking at sort of classical work in visual neuroscience from the 1950s and 60s, the work from Hubel and Wiesel, who are represented at the top here. And what they discovered was a particular way in which the neurons in the visual cortex are connected to each other. And in the early 80s, the gentleman in the center here, Kunihiko Fukushima, had the idea of building a computer model that would kind of simulate this a little bit. But he didn't have access to this backpropagation algorithm I was telling you about. But he still kind of managed to build a sort of a model of the visual cortex that more or less worked. He could kind of recognize simple shapes with it. So one thing I did in the late 80s is invent something called convolutional neural networks. And what those things are basically getting the same inspiration from Hubel and Wiesel, but building a network of this type that could be trained with backpropagation. And I don't really have time to explain exactly how that works, but let me say just a little bit. Essentially, if I can find my pointer, here we go. So take an input image and take a set of coefficients. So here this represents a little set of 25 coefficients. Black is large and positive, white is large and negative, and gray is 0, something like that. And then compute the sum of the products of those pixels by those coefficients. Okay, so we take this coefficient, multiply it by this pixel, and then the next coefficient, multiply it by the next pixel, etc., and compute the sum of all those, right? So it's a weighted sum. And then put the result in that pixel. And then take that window and shift it over and just keep shifting it on all possible positions, and then record the results here on the output. And what you have is what's called a convolution mathematically, but a discrete convolution in that case. But it also looks very similar to what Hubel and Wiesel discovered neurons in the primary visual cortex area are doing. So all those coefficients that are going to be used in those convolutions are going to be learned using this backpropagation algorithm. And what we can do is stack multiple layers of those convolutions. There's another operation here called pooling, which I'm not going to go into, but basically you can stack multiple layers of those, and as the signal goes into the layers, the representation of the input that is computed is more and more abstract, if you want. And you can see this on this little animation here. So this is work that goes back to the early 90s. And here we show a digit. The system has been trained to recognize hand-written digits. And we shift the digits. We see the activations. Each pixel here is the level of activation of a particular simulated neuron in this neural net, this convolutional net. So that's the first layer, second layer, third layer, fourth layer, fifth layer. And by the fifth layer, the representation is kind of abstract. And it has captured a lot of information about the shape, but eliminated a lot of information about the position or the details of the shape. It really knows it's a 3, but independently of who drew the 3 and what position it appears in and things like that. So the inspiration from biology here really is helpful to build those systems. So what happened around 2012, so about 10 years ago, is that people started to use those architectures, very large-scale versions of those architectures, and apply them to not just handwriting recognition, but recognizing objects in images, like, what species of dog is this, right? That happens to be a Samoyed or whatever. So this was our colleague from University of Toronto, Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton, and they basically used our idea, convolutional net, and scaled it up, implemented it on GPUs, which are the graphic cards that are capable of performing lots of multiplications and additions very quickly, and they're very cheap. And so they were able to build a network of this type with something like 1 billion connections. Before that, we were limited to a few 100,000 because our machines were not fast enough. And with that, they were able to really beat everything else by such a margin. So every other technique that people had invented to recognize images, they beat them by such a margin that everybody stopped what they were doing and basically switched to using this. So that occurred around 2013. It occurred a couple of years earlier in speech recognition. So around 2010 or 11, there was you were able to start talking to your phone or to your Alexa or whatever. And that's because people started using those deep learning techniques for speech recognition, and it started working really well. So that occurred a few years before image recognition. And then a few years after that, around 2015-16, people figured out how to design neural nets that could do language translation and basically have some understanding of language. So that created another revolution. So as a result, AI can do some pretty amazing things today. There's a lot of applications in driving assistance and autonomous driving, which is coming on things like online safety and security, filtering harmful content and things of that type, and spam and clickbait and terrorist propaganda or whatever. A lot of applications in medicine and science. So, for example, if you take all the big tech companies today, Meta, which means Facebook, Instagram, etc., Google, YouTube, Amazon, etc., they're completely built around deep learning these days. So you take deep learning methods out of those companies, and they literally crumble. Like all their services are built around it for two things: for filtering content and for ranking content. Basically, for figuring out, is this content going to be relevant for a particular search query, or is it going to be interesting to the person who is just connecting to Instagram or Facebook or whatever? So deep learning basically helps us deal with the information deluge. And it also helps people who cannot use technology in the way most people can. So there's about 3 billion people today who can't really use technology, and for various reasons, because they don't have access to networks or things like this. But 800 million are illiterate. 300 million are essentially blind or visually impaired. And so if you have a system that can read a text to you and kind of, or you can put your finger on a photo and it will tell you what's under your finger and describe the photo, that helps. So to give you a quick idea of how this, what this does, today the automatic filtering systems on Facebook take down, actually my number here is out of date, takes down 95.6% of all of hate speech automatically. In fact, it's 96.1% until the last number. So those things kind of improve. And if you took Facebook maybe 4 years ago, that number was more like 40%. So there's been an enormous progress over the last few years for systems that can understand enough about text that they can do things like content filtering, detecting hate speech or bullying or things like that. It's far from perfect, but it works much better than it used to. And other numbers for different types of detection of objectionable content. Those numbers are published here. This is the URL at the bottom. In computer vision, this is a video that was put together by some of my colleagues at FAIR. So FAIR means, it's called Meta FAIR, and it means Fundamental AI Research, at a company that's now called Meta. And so we have vision systems now that can not just identify objects in photos, but they can track objects in videos, track the pose of people, which actually is kind of important for things like augmented reality and virtual reality. And even essentially do what's called semantic segmentation, which means essentially kind of drawing a mask around every object and background in the scene and label everything completely densely. So, it's not as if computer vision is completely solved, but it works really well to a degree that's really, quite impressive. That system, by the way, is called Detectron 2, and it's open source. You can just download it. This is true of almost all the work that's done at FAIR. It's all published and all open source. Here's another project that's open source, and this one is going to become available soon to a MRI machine near you. So this is a system that was invented by some of my colleagues at FAIR and others other colleagues at NYU in the radiology department. And they figured out that they could use neural nets to improve the quality of the image collected from a MRI exam, and essentially reduce the time it takes to take an MRI by a factor of 4. So instead of having to spend 40 minutes in a MRI machine, which is very noisy and claustrophobic, you can spend about 10 minutes and get essentially the same result. So it reduces cost, it improves reliability, you can give the test to more people. There's been a number of articles about this in the press, but also technical articles. And those systems are now being integrated in MRI machines. This is something that neither NYU nor Meta makes any money with. This was just research that was made public. The code was made open source, and all the machine manufacturers picked it up and basically are implementing it in their machines. Now, what deep learning is doing also, or modern AI, is helping science, particularly things like neuroscience. So people now use those convolutional nets I was telling you about as models of how the visual cortex works, and basically can sort of decrypt a little bit exactly how the visual cortex functions with the help of those models that are kind of somewhat similar in structure with the visual cortex. It's used a lot in genomics. Eugene can confirm, perhaps. He's an expert, I'm not. You know, and biochemistry. So in particular, things like protein folding. So this is a picture from DeepMind, colleagues at DeepMind, of AlphaFold, which is a system to predict the folding of the conformation of protein that has made really sort of big progress over the last 2 years. Since then, there's been like 2 or 3 other systems that do similar things. It's never the case that one lab or one company is more than 6 months ahead of everybody else. Generally, when there is a very smashing result, there is a reproduction of it within 6 months, even if the code is not open source, because people are all working on the same thing, basically. So a lot of work on perhaps using this to design new proteins, so it could help with drug design and things of that type. Other applications in physics, like for filtering particles in particle physics experiments, in simulating the climate, in chemistry and material science to design new materials for things like batteries and other materials, for large-scale simulation in cosmology. So you have some theory about what dark matter is about, and you want to simulate the first instant of the universe to figure out does this theory correspond to what we observe? And so you have to be able to run simulations of the universe at the scale of the universe in the first few years of the universe. You can't do this with traditional methods, but those deep learning methods actually help accelerate that simulation. But here is a really interesting project that was started by some of my colleagues at FAIR. It's called the Open Catalyst Project. It's a open competition and data set. And the idea there is basically there is one way to, there's several ways to solve climate change, but there is one really interesting way to solve climate change. And it's to produce hydrogen with electricity from renewable sources like photovoltaic or wind. The problem with solar energy and wind is that it's not controllable. When there is no wind and no sun, you don't have power. And so you have to have a storage system. You have to be able to store huge amounts of energy so that when there is sun and wind, you store that energy and you can use it, ship it to wherever it's needed, and use it wherever it's needed. Otherwise, you also need regular power plants to pick up the slack when there is no wind or no sun. So what the Open Catalyst project is basically trying to use deep learning to design new catalysts that will make the problem of separating hydrogen from oxygen scalable and efficient. Right now, the techniques that exist for this are either scalable or efficient, but not both, okay? You can separate, you can do the experiment, right? Put 2 electrodes in water, pass some electricity, and you'll get hydrogen on one side, oxygen on the other side. You have to put salt in it or something. And for this to be efficient, you have to put something like platinum, which is incredibly expensive, so it's not scalable. So how do we make this scalable and efficient? And perhaps deep learning can help for that. So this is what this project is about. And it's a collaborative project, it's an open project, so anybody can participate. Anybody who has some ideas about how to go about this can use the data set that is produced by this team and enter. Future applications of AI would be things like, so I might surprise you, but like we all have one of those, sometimes 2 in our pockets. 10 years from now, 10, 15 years from now, we won't have it anymore. We'll have augmented reality glasses that display information and overlay information on top of the real world. We'll have something like this in our pocket, but we won't have a screen. It would just be the computer and the battery, basically. But But everything will be displayed in our augmented reality glasses. And how do we interact with augmented reality glasses? There's basically 2 or 3 ways. One way is you talk to it, and it talks to you. Another way is you make gestures in front of it, but that's kind of inconvenient. And the third way is you wear a bracelet, and the bracelet measures the myoelectric currents from your muscles, and you can have your hands in your pocket and type, essentially. So Meta is actually working on all of those things. But one thing that might happen is you have some sort of intelligent assistant that lives in your glasses, and it's like a human assistant, right? It helps you in your daily lives. It can answer any question you have. It can manage your agenda. It can, remind you where you left your keys, or where you parked your car, and things like that, right? So that will happen probably over the next 10, 15 years. But for this, we need machines that are much more intelligent than they currently are. So right now, the kind of intelligence that we observe that we can reproduce in machine with supervised learning, or with reinforcement learning, which is another type of paradigm of learning, we're not able to produce machines that are as intelligent as humans, certainly, but not even as intelligent as a cat. Okay, we can have AI systems that are very powerful in very narrow domains, but as soon as you go out of that domain, they don't perform very well. So that's kind of called narrow intelligence, if you want. They're trained for one task, and they're just good at that one task. So one question we can ask ourselves is, how do humans and animals learn so efficiently and so quickly? It's kind of amazing how brains of animals and humans, how fast they can learn new skills. And the question is, what's the missing component that we don't have in those learning machines that humans and animals have? And so this is a chart that was put together by my friend Emmanuel Dupoux, who is a researcher in developmental cognitive science in Paris, also affiliated with FAIR. And he has this chart that tries to kind of depict at what age babies learn basic concepts about the world. That the world is three-dimensional, that there are objects that are animate and others that are inanimate. The fact that when an object is behind another one, it still exists. That's the notion of object permanence. And then things like stability and things like inertia and gravity, the fact that when an object is not supported, it's going to fall. That is learned around, probably around 9 months. Some people say it's more like 6 months, but it's around that age that babies learn that objects are supposed to fall. So if you take a 5-month baby and you show the little scenario on the left, where a little car is on the platform and you push it off the platform and it appears to float in the air, they barely pay attention to it. But you show that to a 9-month-old baby, and she goes like the little girl here in the middle because she's learned that objects are supposed to fall and this object is not falling, so it's very surprised. Now, it's quite possible that all of those really basic things that we learn in the first few months of life and first few years, help us learn skills very quickly afterwards. How is it that any teenager can learn to drive in about 20 hours of practice? Whereas if we were to train current machine learning systems to drive cars, the same way people drive cars by trial and error, it would take, basically millions of hours of training. Of course, it would have to be done in simulation, and it would cause, hundreds of thousands of accidents before they would learn to drive, and probably not very well. So the difference is that, by the time we get, we turn 17 or 18, we have a good model of the world in our mind, and we can use that model to predict that if we are driving next to a cliff and we turn the wheel towards the right, the car is going to run off the cliff, and nothing good is going to come out of that, right? We're going to break the car, we're going to kill ourselves, things like that, right? So we have this predictive model. We can predict ahead what's going to happen, and that allows us to plan and not make too many mistakes. And perhaps it's the accumulation of all those models of the world that we acquire in the first few months of life that constitutes what we call common sense, which machines don't have today. So basically, that leads me to 3 challenges for AI and machine learning. Learning representations of the world that would allow the machine to predict what's going to happen, perhaps as a consequence of their actions. Learning to reason, which I'll come to in a second. and learning to plan complex action sequences, which we still haven't figured out how to do, but we have some ideas that I'll talk about. The other analogy here that I have is that the type of learning I told you about is supervised learning. And if we imagine intelligence being some sort of chocolate cake, like a forêt noire or something, the bulk of learning that we do as humans and animals is really self-supervised learning. It's not the supervised learning thing that I was telling you about earlier. It's something else. It's the kind of learning that babies do when they observe the world and they build a model of the world. Supervised learning is probably just a small icing on the cake. This is what we learn, what adults tell us to do when we are little, or give us instruction for what we learn at school, right? And then reinforcement is when we try something and it fails and we try it again. And that type of trial and error learning is very minor, actually plays a minor role. So if we use those concepts, how would we build an autonomous AI system that might have the same type of behavior or performance that we observe in animals and humans? And by the way, there's a long paper I wrote. It's not a very technical paper, so if you're not AI specialist, you can probably read it. You need to be a scientist perhaps, or at least a student. And there's a horrible address for it here at the bottom. I posted a link on just yesterday on Facebook, Twitter, and LinkedIn if you want to look at it. But it explains a little bit what I'm going to say next. So this would be the architecture of an autonomous AI system. And I must tell you now, nobody has really built this. Okay, this is more like a inspirational kind of plan, if you want. This is what I'm going to work on for the next 10 years until my brain turns into white sauce. So the central piece of this is the world model, this part of our brain that allows us to predict ahead of time what's going to happen, or fill in the blanks, information that we don't have yet. I see a lot of your faces, and for a lot of you, I've never seen the back of your face, but I have a good idea what it looks like because I have some prior knowledge about what humans are supposed to look like from the back. So that's what this world model does. It fills in the blank, whether those blanks are missing information that you don't get from your perception, or whether it's missing information that may be in the future, so you don't have access to it yet. And you can use this world model to predict the result of your actions, and so perhaps you can use this to plan ahead, and that's a classical idea from an engineering discipline called optimal control, going back to the 1960s. You need perception, so perception is a way to estimate the state of the world before you can kind of simulate the world, if you want, and imagine a sequence of action. The cost, the red thing here at the bottom, is something that sort of measures how good the result of that sequence of action is using your simulation of the world model. And I'll talk about the other stuff later. So there's two ways to use that architecture. One is for sort of mode 1. So this is by analogy with Daniel Kahneman's System 1, System 2, for those of you who know this. It's basically a reactive action. So you have a perception coming from the world. It gets into this encoder that estimates the state of the world, in some representation. That goes into this sort of yellow module here that directly produces an action. So this is, like subconscious reactive action. You're, playing tennis and you see the ball, coming in one direction, and automatically, without thinking, you react. Or you're driving on the highway and the car goes, a little bit on one side. You don't have to think about it. Automatically, you'll bring it back in the center of the lane. So all the things you do sort of without thinking, okay, without planning. Then there is a second mode, mode 2, and this one is planning. So that requires you to use your model of the world and to predict what's going to happen as a consequence of your actions. So you imagine a sequence of action. You imagine the result of that sequence of actions using your world model. And then you can measure the cost or the quality, if you want, of the resulting state. And then the role of the actor here at the bottom is to figure out what sequence of action is going to optimize that cost, is going to make it as low as possible. Okay? So the cost might be, I'm thirsty, okay? And the sequence of actions to minimize that cost, if I imagine it in my head, would be, I'm going to grab this water bottle, and it seems to be closed, so I'm going to have to open it and then drink from it, right? And then I can decompose this into a reaching motion and a unscrewing motion. And all of this is decomposed down to millisecond by millisecond muscle control. And that's what's called hierarchical planning. So I had a task to quench my thirst and decompose this into a bunch of actions that will satisfy it. I'm actually thirsty. So in this cost has two parts. One part is an intrinsic cost. So this is kind of a hardwired piece of the cost function that essentially determines the behavior of the machine. We have that. All of us have that. Different animal, all animals have this. This is the basic drives that push us to do things. When we're babies, we look at moving objects, or attention is attracted by moving objects. It's because of something like that. When we get older, we seek the company of other humans, most of us. And that's hardwired into our intrinsic cost. Our intrinsic cost measures pain, pleasure, hunger, thirst, all of those things that are hardwired into us by evolution. It also drives us to, when we are about, less than 1 year old, to want to stand up. Makes us very happy to stand up when we're at that age. Okay, it's because there's a cost term that doesn't tell us how to stand up, but it tells us you should be happy if you stand up. And then walking and things like that. So that's what drives our behavior. It drives social behavior as well. So if you have desires of interacting with other people and getting stuff from them, we are a social species, so we need each other to survive, so we need to be able to influence each other. Okay, so we have this capability, and it's because some of that stuff is hardwired into us by evolution. Other animals, very similar to us, that are not social, don't have those behaviors hardwired into them. Orangutans, for example, they're not social animals. So they don't have this drive to influence other orangutans. But as humans, we do. Chimpanzees do. Bonobos do that. Baboons, all social primates and all social animals. Okay, so how are we going to build and train this world model? And this is where things become complicated. And I can't claim that I have the complete answers, but the main issue there is that the world is not deterministic. So if I do an experiment where I take a pen, I put it on the table, I let it go, every time I repeat the experiment, it's not going to do like this video, which is a loop, but it's going to fall in a different direction every time. And so if I want to train a neural net to predict what's going to happen next, it can't predict exactly where the pen is going to fall. And in fact, if you ask it to make one prediction, the best thing it can do is predict the average of all the possible positions of the pen, which is kind of a transparent pen in all orientations. So when you train a system to predict what's going to happen in a video, what you get is this kind of result where you get very blurry predictions here. So this is an overhead view of a highway when you see cars running around. And this is a video prediction system that has been trained to predict what's going to happen. And you get those blurry trails because the system cannot predict if a car is going to accelerate or not. Same thing here, you see a little girl. The first 4 frames of that video are observed, and the last 2 frames are predicted. And they're basically blurry because the system has no idea what the girl is going to do and whether the camera is going to move or not and things like that. So it predicts a blurry mess. So how do we fix this? So basically, the main issue with this is what I call self-supervised learning, or the way to approach the problem. So let's say you want to do video prediction. You show a piece of video to a machine, and you cover the continuation of that video, and then you show the rest. And the machine is supposed to adjust itself to tell the difference between a good continuation of the video and a bad continuation of the video, right? So what you want in the end is a system that when you give it a consistent video, okay, initial segment and continuation, it tells you, yes, that looks good. And when you give it initial segment and something implausible, it tells you, no, that doesn't look good, right? So one way to formulate this is what's called energy-based models. So an energy-based model is essentially a mathematical function, can be a neural net or something inside of it. And you feed it an x and a y. So x is the observed portion of the video, and y is the yet unobserved portion of it. You feed x and y to this neural net, and the neural net has a single output, single number. It's going to be 0 if y is a good continuation for x, or a small number, and then a larger number if y is not a good continuation for x, an implausible continuation for x. And this way of representing a dependency is called the implicit function. Oops. So implicit function is something like this, where you have a dependency between x and y. So here x and y are just numbers. And you have some sort of landscape here where your training samples are those black dots. So you want low energy for those things. Okay, you want f of xy to be small for those things. You want the altitude to be low if you want. And then for everything else, you want the altitude to be higher. And so that's called an energy function. And the good thing about this is that for one particular x, there might be multiple y's that have low energy. So that allows this system to tell you there's a lot of plausible y's here that correspond to this initial x. And it's not a single one, like the pen in all orientations. So the next thing is, how do we train those things and how do we build them? What do we put in that f of x, y box, and how do we train it? So let's talk about how we train them first. So there's basically two classes of methods to train them, contrastive methods and regularized methods. So think of this energy function as sort of a landscape or like a sheet, right, that you can change the shape of by changing the parameters of some neural net. You want to give a good shape to that piece of cloth by making the training sample have low energy and the rest have higher energy. So the contrastive methods basically generate those green points that are outside the training samples, and they pull it up. All right. So you take this piece of cloth, you push down on the places where you have training samples, the blue dots, and then you push up on the regions where you have green dots, and so you get this kind of landscape where the energy function takes the right shape, hopefully. But that's very expensive because that space may be very high dimensional, not just 2 dimension, but it may have thousands of dimensions, and that contrastive method actually becomes impractical in really high dimension. So there are other methods, regularized methods, which I'm going to talk to you in a minute. And basically what those regularized methods are based on is the idea that you're going to design the energy function in such a way that the volume of space that can take low energy is as small as possible. So whenever you push down the energy of certain regions, which would be those kind of pink areas here, the rest has to go up because there is a limited volume of stuff that can take low energy because of the way you design the function or the way you regularize it. And that tends to be more efficient. There is one way in which contrastive methods have been incredibly successful, and it's for natural language understanding. So I'm going to tell you a little bit about this. You might have heard of things like GPT-3 and BERT and things like that, or large language models. That's how people call them these days. So those are systems that are capable of generating text, to some extent understand text. They're capable of translation, translating text and things like that. And the way they're trained with self-supervised learning, and then they are fine-tuned for a particular task. The self-supervised learning phase is very simple. You take a piece of text, typically a few hundred words long, maybe 1,000 words, something like that, and you remove 10 to 15% of the words. You replace them by a blank marker. Okay, so you corrupt the text, and you feed that corrupted masked text to a big neural net, a particular architecture called a transformer, which I'm not going to go into. And you train this neural net to actually recover the full text, so to predict the words that are missing. In the process of doing so, that neural nets will have to capture enough about the meaning and the grammar of language to be able to do a good job at it, right? So if I tell you, it's kind of a thing that we give to school children. If I tell you the blank chases or the cat chases the blank in the kitchen, the blank probably is like a mouse or something, right? You can't say for sure it could be something else, but at least you can have some set of words that you think are likely to appear at that location. So that's what those systems do. They predict a distribution of probability for all the words in the dictionary, and they give you for every word in the dictionary with what probability it can appear at that location. And those systems, pre-trained, can do amazing things. They can, you pre-train on very large data sets, and so this is a system that was produced by my colleagues at FAIR. It has 175 billion of those modifiable connections I was telling you about, those knobs that are adjustable. It has 175 billion of them. Okay, you think that's large? It's among the largest models that have ever been trained, but it's tiny compared to the human brain. Human brain has, probably 10,000 times more than that, if not more. So you train those systems, and they can do things like hate speech detection with fairly high accuracy in multiple languages. They can do all kinds of things, but here is a funny thing they can do. So this is an imagined dialogue between the Statue of Liberty and a person. And what you do is you start typing. So this system has been trained to produce a prediction about the next word in a text. Okay, you give it a text, and you only remove the last word, and you ask it to predict it. So it's been trained on enormous corpus of text, and you type the text at the top in bold character is what the human types. Okay, the chat between the curious humans and the Statue of Liberty. Human, what is your name? Statue, I'm the Statue of Liberty. Human, where do you live? Statue, New York City. Human, how long have you lived here? And then the human stops and asks the system to just complete. System says, I've been there since 1886. Human, what is your job? This is still the machine producing that text, right? Statue, I was built to welcome immigrants to the United States. What is your favorite food? I like ice cream and apples, blah, blah, blah. I mean, those things are almost coherent, but you have to be careful not to get fooled that those systems don't really have a good understanding of the world. They do not have any experience of the world. They don't know that the world exists. They have never experienced the physical world, right? So their understanding purely comes from text, and as a result, their understanding is very shallow. And so they can say very stupid things sometimes. They're not the answer. They can fool you into thinking that you're talking to a human, but they, in fact, are not. Now, there's been a story the last couple of weeks of this engineer at Google who was playing with a system of this type and basically claimed it was conscious and sentient and blah, 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 and revealed that to the outside. And everybody at Google and everybody in the AI community said, this guy is nuts. There's nothing like that going on. And they basically fired him. I mean, they didn't really fire him, but they told him to stay home. Okay, so let me speed up a little bit. So basically what we're going to use as a world model is an architecture called JEPA. So that means Joint Embedding Predictive Architecture. And what it does is that you give it an X, so initial segment of video, and a Y, the continuation. You run those two things through two neural nets. They extract representations of both X and Y, and then you run that through a predictor, which is another neural net that makes a prediction about the representation of Y. And you're training the system to make good prediction, but also to extract representations of the world that contain the juicy part of the information about the world and basically eliminates all the stuff that is either too complicated to predict or useless. So this is called it's a special case of joint embedding architecture. And those things have been used for a few years now for essentially pre-training either speech recognition systems or computer vision systems. I'm not going to go into the numbers here. Basically, this is to show that when you pre-train an image recognition system using this kind of technique, those joint embedding architectures, by basically showing it two versions of the same image, one is a slightly distorted version of the other, and then telling it this is the same object, so produce representations that are identical, and then you also force it to produce representations that are different for different images. You pre-train the system this way, and then you fine-tune it to do a particular recognition task. They work better than if you just train with supervised learning completely. So the revolution that you probably perhaps haven't heard about before in AI that occurred over the last 3-4 years is a revolution of self-supervised learning, particularly for natural language processing, but also for image recognition and speech recognition. So the little speech recognition systems at Meta are pre-trained using this type of self-supervised learning. I don't have time to go into the details, but the result is that you can now train a very accurate speech recognition system with about 10 minutes of label data, which is very interesting because that means now you can have speech recognition in hundreds of different languages. It really wasn't possible before because you had to have a separate speech recognition system for every language and every accent. And now basically you can have one gigantic neural net that accepts every language, hundreds of them, and does speech recognition accurately for hundreds of languages. Okay, I'm going to spill the beans. Tomorrow, my colleagues at Meta are going to announce a new system called No Language Left Behind. And it's a system that can translate 200 languages from any direction, any of the 40,000 directions. Real time, from speech to speech. It's pretty impressive. Okay, so we're going to train those JEPA architectures, and I'm not going to tell you exactly how we do it, because that would be a bit too complicated. It's just that they work. The trick is, there's a trick here that we use to maintain the information content of those representations so that they contain as much information as possible about their input that they can. And I'm not going to bore you with result. There's applications that are being started of this to things like medical image analysis and things like this. Because there's a big problem in medical image analysis. You don't have a lot of training data. So we'd like to be able to pre-train the system as much as possible. Okay, one cool thing about those JEPA architectures is that you can stack them in a form that's called hierarchical JEPA. And this is very important if you want to have systems that can do the type of planning I was telling you about earlier. So, you know, have an overall goal, and you want to decompose it into sub-goals, and then you want to decompose those sub-goals into kind of sequence of actions or sub-sub-goals, all the way down to muscle control or motor control for a robot, for example. That kind of hierarchical planning requires multiple levels of abstraction to represent your task, and those hierarchical JEPAs are basically a way to approach this. And I can't really explain how that works for two reasons. First, because I don't have time, but more importantly, we haven't built this yet, so we don't know if it works. At this stage, it's an idea. So I've come to the conclusion. So the next step in AI, or what I call autonomous AI system, is going to be a massive use of self-supervised learning that will allow machines to learn models of the world by observation. Those systems have the characteristic that because of energy-based model approaches, we'll be able to handle uncertainty in the prediction. And they're going to be able to plan and reason, essentially, by the planning is a form of reasoning. This is mysterious thing called a configurator here, which I'm going to skip for now. And that leads me to my last slide. You know, prediction really is the essence of intelligence. This ability to fill in the blanks, predict the future, even predict the past from the present, or retrodict, I should say. That's really the essence of intelligence. And then the second essence of intelligence is using this ability to predict to plan a sequence of action to arrive at a particular result. Almost everything is learned, most likely. Like there's a big debate of, you know, how much needs to be hardwired in the system for it to become intelligent, like the same way we have things that are hardwired in our brain by genetics. How much do we need to hardwire in our intelligent systems? You know, we're probably going to use those hierarchical JEPA architectures and those intrinsic cost function I was telling you about kind of drives behavior and determine what we learn. And reasoning is an extension of simulation, prediction, and planning, essentially. And then this last thing, consciousness. So I don't have much to say about consciousness because nobody knows how to define consciousness, and a lot of scientists stay away from it because it's too much of a controversial topic. But basically, in this model here, at the top here, there is a mysterious module called the configurator. And what this configurator does is that it configures the entire agent to solving the task at hand, right? So if I have planned this idea that I need to drink a sip of water, you know, I have to concentrate on this task and you know, I can talk at the same time because it's not too complicated of a task. But if it was a more complicated task, I would have to completely concentrate on it. And the reason is because I would have to use my world model for that. I only have one world model. I don't have one world model. I have one world model engine. And my world model engine is configurable by this configurator so that I can, you know, I can configure it for the task that I'm currently solving. But because I only have one world model engine, I can only attend to one task at a time. This is why humans, at least men, can only attend to one task at a time, until women can do multiple conscious times at a time. I wouldn't know. So this is a bit of a crazy hypothesis, which is that the illusion of consciousness is given to us by the limitation of our brain, the fact that we have a single world model simulation engine, and we need to be able to configure it, so we need some sort of overarching kind of module that oversees or, you know, executive function in our brain, and that's what gives us the illusion of a consciousness. I'm not sure at all, like, this is complete speculation, this is probably wrong, but it's fun to think about. Thank you.
There should be many questions to Professor LeCun. He really covered a lot of ground. Please. Oh, okay.
I have a small question. So what's about causal inference? And because it's not just about prediction, but it's also about causal reasoning. What if we choose this and you win this, but you choose?
Okay, so there is some provision in this for for establishing causal relationships, which is when the system learns a model of the world that includes its own actions, that model is causal, right? Because it predicts the resulting state of the world from the current state that results from taking an action. That's a causal model. Now, you want a causal model that's more powerful than this. You want, and I have that in the one of the architectures, those Z variables here that I haven't talked about. Those are latent variables, and those latent variables can represent hidden causes that you don't observe directly, that might explain what you observe in the world. Okay, so if the system does a good job at kind of figuring out what are underlying causes to objects by inferring those latent variables, then basically it does causal inference.
One question I would have, it relates a bit to what you just said, is that there are many arguments to think that in biology, when objects learn, they learn because they also interfere with the process they investigate, so to speak.
Yeah.
And so what would be a way for you to have these reciprocal interactions,
right,
where the system can not only collect information but also interact with it?
Also interact, yeah, absolutely. So I allude to this in the paper, but there's basically, you can think about several modes of information collection. So one is just observation. So, you know, babies up to 3-4 months old hardly have any way of influencing the world other than their own body. But the rest of the world, they basically have no influence.
They do cry a bit.
Well, they can cry to, you know, get fed and things like this. But the rest of the world, like, you know, they can't move an object that's, you know, some distance away because they can't get to it, right? So, so most of the learning that takes place there is largely observation. Now, what they can do is move their eyes, though. So that's a little bit of active information seeking because they can choose to attend to certain things and not others. They are moved around, and, you know, at some point they can move around, so they can get different viewpoints from the same thing. They have 2 eyes, so they get 2 different views of the world. From that, they can probably infer that the world is 3-dimensional, because that's the best explanation for why the view of the world changes from one eye to the other, or when you move your head. So those basic concepts probably are learned really, really quickly. And then when you start being able to interact with the world, you can do experiments to verify your hypotheses, right? So around 8-9 months, you know, you put a baby in a high chair, and you put a bunch of objects in a high chair, and the first thing they do is they throw them on the floor because they're learning about gravity, right? So they're kind of verifying that every object actually falls, right? It's very annoying for the parents, but they do that for a good reason. And then, play is basically that. So, and then there is, learning new skills, like, you're learning to ride a bike or something. There is a bit of, reinforcement learning taking place there. A lot of usage of your model of the world and interactions. So there's, all those levels of interactions, basically. But a lot of it is just passive observation.
Yeah. So I want to ask about the model for autonomous AI, for the configurator part. So I read the paper that was published yesterday, but I didn't understand how practically it can be implemented, like how potentially the configurator can configure each word model and the other models to learn set goals or specific goals.
Okay, I'm probably going to say things that most of the audience is not going to understand. But the basic proposal, which actually I allude to in the paper, is to use transformer architectures for the predictor and for the configurator itself. So the configurator basically would be feeding extra tokens as input to a transformer that would be the predictor in the JEPA architecture. And it would modulate its function. And then, the question is there a need for some specific mechanism to train the configurator other than just backpropagating gradient to it so that it configures all the modules for the right thing? That I don't know the answer to. Okay, but there's a bunch of work on this in what's called meta-learning that people have thought about this before.
Thank you. Fascinating, absolutely fascinating. I think a lot about biases and where they crop into the systems. And it seems that the model has a lot of different entry points for that. But also interesting that it looks at culture, your model of predictability. Different cultures will predict sequences of actions in different ways, and also you mentioned the issues of emotion, on how they affect the cost, of the structure that you're modeling there. So if culture and emotion and different types of data will be coming in, where do you think potential biases will appear? And how can they be, prevented when you're developing these new, approaches?
Okay, that's a vast topic. But okay, first of all, if you train a system, you don't have to have this kind of sophisticated architecture. You train a supervised learning system. The system will reproduce the biases in the data, and sometimes will accentuate them for reasons that are sometimes, relatively easy to understand. But it will basically, develop good representations and features for things, for the type of objects that you train it on very frequently, and for the type of objects that are presented infrequently, it may not develop the right features for it, and it will not work very well for it. So for example, you take a representative sample of the French population of, picture the faces, and you train a face detector. It's going to work better for white people than for people of, African or Asian descent, just because there is, fewer of them in the training set. So there's an easy way to fix it, which is that you try to have a balanced training set, that you have, more or less the same number of people of different categories if you want kind of similar performance for different people. People themselves are subject to those biases too, right? I mean, we're better at recognizing people from, ethnic groups that we grew up with, basically, right? Regardless of whether it's the same ethnic group as ours or not. So, so we have those biases. That's a side effect of learning, any kind of learning, whether it's machine learning or human learning. And the question is, how do you kind of prevent bad side effects of this when you deploy those systems for practical applications? It doesn't make stupid decisions that hurt people. It's a whole field now called responsible AI, fairness in AI, whatever. It's a whole field. I'm not a specialist of it. It's an entire field. Now there's the question of that you asked about culture and emotions. So those systems I mentioned, I didn't say this in the conclusion, but they will necessarily have emotions because emotions are anticipation of outcomes, essentially. If I pinch you, it's going to hurt, right? And you're going to be very surprised that I just pinch you. If I approach you again, now you're going to recoil because I'm going to pinch you, right? So that's because now you've developed a model, a predictive model that says, I'm going to get pinched. And so you have an anticipation of the result, which results in a little bit of fear, essentially, right? So if we have systems that are built on this model that have a cost that is optimized by behavior, they will necessarily have emotions. There is those science fiction movies where the commander Data in Star Trek has a emotion chip that you can turn on or off, right? That's not going to happen. If you have autonomous intelligence, you have emotion. It's necessary. Culture, we're very far from this. We can't even build things like this that are as smart as a cat. So before we talk about culture, we have a few years.
Actually, culture would be an essential element there because, for example, you're mentioning the movement of your hand to grab. And you started with the number 3, showing us the number 3. Count to 3 with your hands in different cultures.
Yeah, right.
1, 2, 3. 1, 2, 3.
Right.
They are the, so.
Being French and American, yes. The French do this, the Americans do that. Yeah.
So your predictable model, your predictive model, your sequential action will have to be different.
Sure.
According to culture. So I'm intrigued about this concept of how you're going to tackle that.
I'm intrigued too, but in the list of 753 things to do, I think this ranks. We have so many problems to solve before we can get to the point where this would become an interesting question. It is already an interesting question. We just don't know how to, apprehend it at the moment because we're too far away from it yet. It will come. It will come.
Hello. So my question was, when we learn as humans, in general, we have different structures around us to build our own word model. On the other side, the deep learning community has developed a lot of model, and most of the time we did like some Sparta. So as soon as we have a model that works better than the previous one, we just throw it out a cliff, and we use the last one. So the question is, to build really a word model that could be as complete as possible, wouldn't it better to use some models that were already doing the best in general in the past on a specific task, and have an ensemble of them to train a new model?
Okay, what you're describing is already happening. So those self-supervised, pre-trained models in NLP. So it used to be, for example, at Facebook, 5-6 years ago, we had something like half a dozen different neural nets that were used to do image recognition for various tasks, right? So you would upload a photo on Facebook or Instagram, and it would, within 2 seconds, it would go through 6 or 7 different neural nets that would, one would do, violence detection, the other one would do nudity detection, the other one would do, recognize the objects to figure out if it's interesting to you, things like that. Now it's just one big one, and that big one has been pre-trained in self-supervised manner and then fine-tuned for all the specific tasks that people, within Meta wanted to do. And it's hundreds of different tasks. Sometimes, Louis Vuitton will come to Facebook and say, how many people wear Louis Vuitton bags and all the pictures that are uploaded on Instagram? And we can actually answer that question. Okay.
First, I'm here.
Oh, sorry.
First, thank you very much for the talk and sharing your ideas. I'm really thrilled to be here, especially since I came across your paper yesterday and printed out first thing in the morning.
Oh, I feel I should apologize for that.
My question is about alternative approaches towards the future of AI. I know a lot of researchers works towards resurrecting symbolic AI and then combining it with neural networks in one way or another. So I'm curious about your opinion about this line of research, and do you think it will succeed or not?
Right.
Broad
So
question,
you read the papers, you probably know my opinion on this. Also, if you follow me on Twitter, you probably know. But there are sort of 3 alternatives that some people are kind of pushing or thinking might work. So one of them is just take those large language models I was telling you about that are trying to predict the next word and train them not just on text, but also on images and also on video and also on audio and everything. And make them big enough that somehow some magic will emerge out of it. Okay, so that's the scalers, people who think we just need to scale up the current models that we have. We don't need any sort of major conceptual new idea. Okay, I don't believe in this. There's another category of people which is quickly disappearing. A lot of them were at DeepMind, or still are at DeepMind, who believes that you can just figure out how to make reinforcement learning work better. So reinforcement learning is what is used to train systems that play games like Go or chess or things like that. You don't need to supervise the system. You don't need to tell it exactly what move to play. You just have the system play millions of games against itself and then reinforce a strategy that wins every time. And eventually the system, after millions and millions of games, kind of gets much better than humans, which doesn't show that those machines are incredibly smart. It just shows that humans just suck at Go and chess. Okay, we're just bad. We're just terrible at it. Much worse than we thought we were. So I don't believe in this either, because to me, reinforcement learning is a cherry on the cake. So there's just so little information you get every time you do a trial, and the universe tells you if the trial was successful or unsuccessful. Those things don't work, for example, to train a car to drive itself. They don't work to train even a robot to learn to grasp objects, at least in their current incarnation. There's people who are working on making them work, and they all use world models. So people like Sergey Levin or Peter Abil or Chelsea Finn in California, they at Stanford and Berkeley, they use those what's called model-based reinforcement learning. So I think it's an essential component. I don't believe in just scaling up RL. There's a famous paper by David Silver, who is one of the those famous people at DeepMind, that says reward is not enough. Reward is enough, and in my opinion, reward is not enough. Okay, so it's basically advocacy for reinforcement learning. There's a third alternative, which is people like Gary Marcus or early Davis and people, some of them from the previous generation of AI before machine learning became so prevalent. And what they are advocating for is a direct hardwired ability to manipulate symbols and do symbolic reasoning. So they say the future of AI is a combination of deep learning system and explicit symbol manipulation. And the problem I have with this is that, first of all, they don't say how, but also symbol manipulation is an essentially discrete combinatorial thing, which is incompatible with deep learning. So I want a type of reasoning that is compatible with deep learning, and basically that's what my proposal is. So whether this type of reasoning, by figuring out a sequence of actions or latent variables that minimize the cost, whether they will consider this as good enough for symbolic reasoning, I don't know, because they haven't yet read my paper and answered to it. But that will be coming in the next week or two, probably on Twitter.
A few time ago, the EU Parliament just voted a law called Digital Service Act, when they try to target platforms such as Meta and so on. And they want to know how an algorithm works, like in production. When you build this kind of word model, for example, how is important the explainability of the model, and how can we monitor what is actually being trained and was trained before?
Okay, I have a simple question. I don't know if you have a dog or a cat. Do you have any idea how their brain works? Do you have explainability of your cat or your dog? Do you have explainability of your taxi driver? Do you have explainability of even your doctor, right? I mean, your doctor is going to tell you something, okay? He's going to try to rationalize why, she made a decision about something, but it's a story. It's a story to convince you, but it doesn't need to be correct. So, for example, it's notoriously difficult to diagnose appendicitis. And a lot of it is, pressing on the abdomen in various places and seeing how the patient reacts. And you can't just formulate this in words, right? You can't just say, like, you have appendicitis because of this. It's just like, I get the feeling that this is one of those, right? So explainability, we don't have explainability today. We treat bipolar disorder with lithium. We have no idea where it works. Absolutely no idea. So, as long as something is thoroughly tested, we don't necessarily need an explanation for why it works. There's people who argue that we don't even know why airplanes fly. I mean, it's not entirely true, because we understand a lot about why airplanes fly, but we don't understand all the, chaotic behavior of, the air near the surface of the wing, for example. Requiring explanation for AI algorithm, the consequence of this is the law will have to be changed or not enforced, or Europe will just not have AI systems. It's as simple as that. And you know, it would be very sad, right? Because it's kind of the future of industry. So it's just not good. It's not possible. I mean, we're going to have systems that are so complicated, right? They at some point, they're going to have human-like intelligence. Like, how do you explain in details what decision a system like that makes? Like, I can give you the whole list of, you know, a few thousand billion weights, but like, what, you know, does that explain anything? Like, there is nobody at Meta that can explain you in all terms exactly how the ranking algorithm works. That shows you what you know, items on your newsfeed or Instagram. And the reason is because it's a machine learning system. It's a neural net. I mean, it's got all kinds of input to it, but it's a big neural net. You know, and it's a big neural net that's trained for you. So I'll have a different model. I don't think it's possible.
Earlier in the talk, you mentioned deep learning and deep CNNs being used as analogies for the way the visual cortex works. And I'm a little confused because you kind of just implied that explainability wasn't really relevant. So explainability as applied to deep CNNs, you implied it was relevant, but you, in the context of EU regulation of commercial activity.
Well, it depends what level of explainability you want. And that's thankfully not defined by the European law. So, I mean, I'm not a legal expert or anything, so I can't tell you, but the type of experiment that people do in neuroscience these days, visual neuroscience, auditory neuroscience, and also people who study the understanding of language in people, is that they put someone in an MRI machine, functional MRI machine, and they take a convolutional net, let's say, that has been trained to recognize images in various ways, and then they train a predictor to try to predict the activity of the brain from the activity they observe in the neural net, or vice versa. Okay, and the degree of prediction is what they call the brain score. So it's basically how predictive is the activity in the neural net of the activity in this particular area of the brain. And what happens is that the brain score for the lower level in the convolutional net is high for V1, which is the primary visual cortex area in the back of your brain. And then a few layers up, it correlates pretty well with V2, which is like, you know, one layer up in the hierarchy of the ventral pathway of the visual system, and then V4, and then the inferior temporal cortex, things like that. So there is this relationship that as you go up the layers in the convolutional net, you have a better prediction of what you observe in fMRI experiments, in the kind of similar areas. There are things like that also for language understanding. So this, actually the recent paper by a colleague called Jean-Rémy King, K-I-N-G, he works with neurospin, and he's done some experiments of like trying to see to what extent people can make long-term predictions of what's going to come in a text, for example. And what he discovered is that people make much longer-term prediction. They're able to make much longer-term prediction than what those large language models can do, for example. So there are things that we are uncovering about how the brain represents data using those models. That's very interesting. There's literally thousands of papers on this now. It's not just a small group. It's a lot of people.
Do you think the training of such a word model can be finite? Will we reach sort of an equilibrium with it?
What do you mean by finite? You mean a finite amount of data?
Is the training going to end at some point in time, or will we have to retrain it each time?
Well, we can improve it every time. I mean, the thing is, one reason that we retrain, the gentleman was asking that question earlier, new models every time, it's because we come up with new ideas and new architectures and bigger computers and, you know, like new ways to implement this in software and all that stuff. So, you know, we retrain those big models because ideas evolve. But let's say we stop coming up with any new idea, we'll still be, I mean, basically we would, you know, train some giant neural net essentially once and then just fine-tune it for whatever task that we need. Some of those large language models, you know, are more or less being trained on like all the text that has ever been available online. So, like, you know, you can't have bigger data sets anymore. It's really huge.
In one of the answers, you said that you want to use transformers to feed tokens, and if I'm not wrong, you present BART, the architecture of BART. But do you have a decision which architecture you will use in your model? Because I saw that in your graphic you had GPT, you present BART, and other, but there are many. So which one do you did you decide to use for your new model, and why this in the prediction?
Well, there are two large families. I mean, there used to be three, but now it's more or less two large families of architectures for neural nets. One is convolutional nets, which I went into. So convolutional nets have the characteristic that they are equivariant to shift. So that means you take an input, you shift it, the output also shifts, but otherwise it's unchanged, at least for a single layer. Right? When you stack layers, it's more complicated. And that is interesting when the input data comes to you in the form of a multidimensional array where motifs can appear anywhere. So an image is typically like this, right? You have an image and you can have motifs or parts of objects that can appear anywhere in the image, so you want to be able to detect them regardless of where they are. For that, you want to use a convolutional net. And the other characteristics of those data is true of speech data as well, is that the correlations are local. So if you take a typical image and you look at how often two neighboring pixels are the same color, it's pretty frequent. But if you look at how often two pixels that are far away from each other are the same color, it's pretty rare. That means there is short range correlation. Neighboring pixels are more correlated than far away pixels. For that, you want to use a convolutional net if you have this kind of data. Now, text is not like that. For text, you can have dependencies between words that are very far away from each other. Take a sentence in German, for example. You have like all the nouns and everything, and then the verb is at the end. Okay, so you can have like a long distance between things that matter. When you're telling a story, you might refer to a character in the story that you talked about 2 pages before, right? So there you want long-range interactions, and for that, a transformer is good because the characteristic of a transformer is that you feed it a bunch of tokens, typically words. The result is equivariant to permutation. So if you permute all the words, you get a result that is permuted but otherwise unchanged. And that actually turns out to be good for text and a lot of things. A lot of things that are kind of object-based type reasoning, this is good. So these are the two big categories of architectures that people use today. And you combine them in various ways. And you know, computer vision systems tend to use more convolutions. And NLP, natural language systems, tend to use more transformers. But there are lots of ways to combine those. There used to be another category, recurrent neural nets, but they're not used so much anymore.
Thank you.
More questions? Oh. All
right. Yeah, I just didn't quite understood how you think about, like, you want a model of the world, but the main issue we have in deep learning is data. How do you? I don't understand how you think your model would. Like, you need to feed all the data of the world to predict any kind of action. How do you manage data for that kind of training for such a model?
Just have it watch YouTube for, all day. Okay.
Just YouTube to predict drug.
Or TikTok or Instagram, whatever, right? Facebook Reels or whatever. I mean, whatever data source that you have for videos that is sufficiently rich in terms of what goes on in those videos. So TikTok may not be a good idea because it's all or Instagram for that matter, but there's maybe a bit more diversity in YouTube. The point is, there is way more data on services like YouTube than you could ever use to train such a system.
So just by using YouTube, you could predict any kind of action, and
that's the hope. Or at least the initial phase where you just get the system to learn a model by observation. So this would not be a causal model that would where the system would be able to predict the result of its own actions. It might be able to predict the result of other people's actions because it would observe it on YouTube, but you would need, in the end, if you want the system to be able to act in the world, you need it to be able to interact with the world. This is the question that was asked earlier. So there you would need a robot of some kind. It could be simulated. It doesn't have to be a physical robot.
Additional questions or comments, perhaps?
Arguably, we could say that potentially humans have such a great ability to learn also because they have a self-awareness. Do you see self-awareness important and present in your system?
I would be happy if by the end of my career we get to the level of a house cat. So I don't know if a house cat has self-awareness.
That's very difficult to determine, and to
right.
and to say it's difficult to say they don't have it, right?
That's true. Or I don't know, octopus.
Same thing.
That's right.
I mean, if you look at a single cell, the ability of a single cell to be self-aware of the mistakes it itself make is already great.
Well, it's like self-regulation or autopoiesis, right? If you want to use a pedantic word. At one end of a spectrum, a thermostat, right, is autopoietic, right? It maintains the temperature. And then at the other end of the spectrum, there is self-awareness. So, like, where do you put the limit as to, like, what we call self-awareness?
It's probably difficult to determine.
Yeah, I mean, so probably, humans, dolphins, elephants, have it. Cats, we don't know. Crows, we don't know. Octopus, we don't know. And a mouse, not clear. Now, we have the biggest computers that we have now to simulate large neural nets. The size of the neural nets we have are about the size of a mouse brain, roughly. If we make an assumption of equivalence of one of those simulated synapses is equivalent to a real synapse, which, of course, is probably not the case.
I had just a very pragmatic question. So I'm surprised that autonomous driving is not solved yet, because I guess you can train algorithm with like all possible accidents and distances, velocities, turns, etc. So what slows down this? Okay, so it's a very difficult problem, and basically what's going on right now is the companies that are closest to delivering on autonomous driving, on full autonomous driving where you don't have a driver at all, right? So a taxi service, for example. They just engineer the hell out of it. So they put all kinds of sensors that humans don't have access to, like LiDAR, for example, which are range sensors. They map the entire domain that the cars can drive in, so they know exactly where the stop signs, the street lights, and everything are. The only thing the perception system have to do is detect other cars, pedestrians, construction, things like that, things that are not in the map. But they can sort of position themselves. And they're very carefully engineered, which is why it's taking so long, because all those pieces have to be engineered and sort of put together so it works. But there's a number of companies that already have pilot programs. So Waymo is one of them. That's a subsidiary of Alphabet, the company that owns Google. There is Cruise. So Cruise is a subsidiary of, I think, General Motors. And they have a pretty good self-driving system now that offers kind of a taxi service in San Francisco, but it's limited to San Francisco. It's pretty difficult to drive in San Francisco. Waymo does this in Phoenix, which is a lot easier. And there's a few other companies that have kind of promising systems. Here is the issue. Those things use basically imitation learning plus classical planning. So imitation learning means have hundreds of drivers drive cars in hundreds of countries, or dozens of countries,
okay, and record the video and the action of the person, and then train a neural net to basically produce the steering angle and pedal action from the images. And that works to a point. It's not reliable enough, but it will. A system like this might work pretty well to, drive a car on a highway, okay? And a lot of cars now come with autonomous driving on highways, right? I mean, you have to keep your hands on the wheel, but they do a pretty good job at it, and they all use convolutional nets, and they all look out the window, and basically many of them are trained this way. The problem with fully autonomous driving is there's always situations you will encounter that the system has not been trained for. So, for example, the people at Tesla were surprised once because they trained the system to, when you have a bicycle, you want to detect the bicycle, and if the bicycle is going in orthogonal direction, you want to brake, right? You don't want to hit the bicycle. Now, of course, there's people who carry the bicycle in the back of their car, right? Now you have to train your system to detect that this bicycle is actually on the back of the car and it's not dangerous. So there's all kinds of situations like this. There's famous accident also of a Tesla car many years ago. This was back when Tesla was still using radars. They don't use radar anymore, but they use a combination of vision and radar. And the problem with radar is that radars have to eliminate static objects from the scene. They only detect moving objects. And what happened was the guy was asleep at the wheel or something, and the car was driving at 130 kilometers an hour, and there was a white truck across the road, and the radar didn't see the truck because the truck was not moving relative to the scenery, and the vision system didn't see it because it was all white, and basically they thought it was the sky, and the car went right under the truck and basically sliced the car away, and so that was kind of a famous accident that was due to a case that basically was not envisioned. Now, what's going to have to happen is for completely autonomous systems to be accepted by the public, they will have to be way more reliable than humans. So human drivers cause one fatal accident every 150 million kilometers, roughly. Okay, so if you want to test a system so that you can prove that it's reliable, let's say 5 times that, okay, you will have to drive it for 6 million kilometers, right, or whatever the number is, and that's or 7.5 million kilometers. I'm sorry, that's, or you have to drive 7.5 million cars for or whatever it is, right? And so now becomes the problem of testing, and how are you sure that all the situations that could ever be encountered will be encountered during that testing? It's a little bit the same problem as putting a drug on the market, like a new medicine. You first test it on a small number of people, and then you expand just to make sure that there is no side effects, and then years after you can realize there are side effects that were not that great. So it's going to be kind of a similar issue, but those problems are being solved and engineered. So we'll have self-driving cars. Eventually, we'll have self-driving cars that might be built around models of the type that I described, which would basically learn more like humans in the end. So those will not need to be as carefully engineered as the current approaches.
Yes. First, just a remark about the last question. I think that because you cannot explain the decision of the artificial intelligence, she can just help you, but she's not taking the decision. You're taking the decision, and she's helping you. So that's why maybe it's not going to be fully automized. And
so that statement is not true.
You don't think so?
No. I mean, right now, AI systems are making decisions completely automatically without human supervision by the billions per hour.
Yeah, of course, but
right?
When you have responsibility and human lives, you take the action.
No.
Of course, you don't take the action.
No.
And for example, if I'm not drunk and I'm driving my car,
yes,
maybe I drive better than when you do the mean of percentage of accidents, and maybe I'm better because I'm not better than the mean just here. So I want to take my decision. I don't know if you.
you know, I think the automated systems will not be put on the market unless they are more reliable than people. So,
Yeah, okay.
and if they are, usually the best combination, like for example, for finding tumors in medical images, which is an application where those vision systems are really good at. Generally, they're better, like if you test them completely separately from humans, they're better than humans at detecting like, you know, breast cancer in mammograms, for example. But the best thing is a combination of humans and machine. You get the best performance if you combine the two. But this is for, you know, life-threatening situations. Most of the decisions that are made by AI systems today are things that don't matter that much. It's, you know, things like you just buy something on Amazon or Fnac or something, and then Amazon and Fnac shows you some other product that is related.
They are helping you, but you take the decision.
Well, but the decision of what to show you is not made by a human marketing person. Okay.
Okay. Okay, that was not my question, but my question is, I know that this system is more and more consuming energy. Is it a concern?
No, it's not.
No?
Okay. I can tell you why. The entire energy consumption of the entire IT industry, so it's not just AI, it's all computers and data centers and switches and stuff like that, is a few percent, on the order of 3 or 4% of all electric power consumed. Okay, so it's
but
not negligible.
It's going up, and
it's not going up.
It's not going up.
It is not going up because it's limited by economics. So if you look, for example, at how much power is consumed by Meta or Google. Google actually wrote a very long paper on this, and Meta also has similar papers, but Google has a very detailed paper. And they give you the prediction of how much energy consumption is going to evolve over time. And it's basically going to be flat. The reason it's going to be flat is because it's determined by how much money Google makes. And that isn't growing very fast. So it's determined by economics. Now, the amount of computation that goes into it grows exponentially because computers are getting exponentially faster, but they're also getting exponentially more efficient. Okay? So let me take an example. You know, there's some articles were published in the press about the fact that when you train one of those very large models, like OPT75B, which is the large language model trained by my colleagues at Meta, the carbon emission of this was estimated. Now, first of all, the carbon emission of this is essentially zero because all of Meta's operations are carbon neutral. But there are still emissions that they buy, compensations for it. But if you look at the real CO2 emission from this, it's equivalent to about 1/3 of a transatlantic flight. Okay, and how many transatlantic flights are there per day? It's 1,700. Okay, so we can train several thousands of those models for the CO2 emissions of 1 day of transatlantic flights. It's really not that much.
Thank you.
Okay, I think it has been a very intense discussion. And Professor LeCun has been exercising his very natural intelligence throughout the long evening. I think we thank him again, and thank you all very much for great questions and data.
Thank you.